Okay, so my name is Shravan Vasisht. I'm a professor of linguistics at the University of Potsdam, and I'm going to walk you through this talk titled The Amazing Saga of the Chinese Relative Clause, a Cautionary a Tale for Tomorrow's Psycholinguists. I'm giving this talk at the conference in Indiana, but I can't do this live because I will be coming back from dialysis at the moment that you guys are supposed to watch this talk or hear this talk. And so I decided to record the talk in advance. You can watch it, and then we can have a 1 hour long question and answer session that we can do live, right? Okay, so the story that I'm going to tell you now can be recreated if you look at the code and data that I provide here, right? If you go to this website, you'll find all the materials that you need. It's these materials are actually sitting on GitHub. So here's the website, github.com Vasisht /ARL Vasisht. This is a paper that I just that's coming out very soon this year, and it basically summarizes the main points that I want to make today. Okay, and you can reproduce all the analyses that I'm talking about today using either this RMD R Markdown file. This is the precompiled HTML code that shows up as an HTML output, or you can recreate all the analyses in the paper that lies behind this code. Okay, I will point you to the paper as well as I proceed with my talk. Okay, so let's get started. And what I want to talk about today is the problem with psycholinguistics, that we are continuing to use methods incorrectly. When we do statistical inference, the approach that we use for data analysis is essentially meaningless. And the main reason why the approach that we standardly use is meaningless is that the assumptions of the methods that we use are not being respected, they are not met. And so what we get from the statistical analyses that we normally do is some numbers, but those numbers don't mean what we think they mean. Yeah. And so more specifically, the issue I want to bring to your attention is that when statistical power is low, the standard frequentist methods that we use, they don't really work, right? Now, I'm going to demonstrate to you that pretty much almost all of psycholinguistics has suffered from this power problem, this low power problem. But today, because this conference is on Chinese, related to Chinese linguistics and psycholinguistics, I want to focus on a very famous set of examples from psycholinguistics involving Chinese relative clauses, right? So I will walk you through what can go wrong in these kinds of data analyses when you dig deeper into what the issues are here, okay? I will also point you to an alternative way to do experimental work and statistical inference in psycholinguistics. I think that that's a much better and much more defensible way to do data analysis. But you can look into that if you're interested. Today, my main point is only to point out that the way we do things in statistical inference just don't cut it. They just don't work from a statistical perspective. Okay? That's the main point. Okay, so here's the main statistical point that I want to start with. This is where everything breaks down. You know, the whole story kind of breaks down here. When statistical power is low, the frequentist methods don't actually do what you think they do, right? And I will show that to you. So let's take the example of Chinese relative clauses. There are several famous papers on Chinese relative clauses. Two of them come from Ted Gibson's lab. And so I'm going to use data from this Gibson and Wu paper from 2013 in Language and Cognitive Processes. It's called Language, Cognition, and Neuroscience now. That journal has changed its name. But the basic idea that most of these papers, take up is they want to compare the reading times at the head noun in subject versus object relative clauses. And because in Chinese relative clauses, the relative clause is prenominal, all the interesting action that precedes the head noun basically leads to a difference, a predicted difference in reading times between subject and object relatives. Maybe I don't need to spell out the underlying story here, but very briefly, the idea that Ted Gibson was pursuing was that inside the subject relative clause, this A condition, this head noun has a gap over here, right? Inside this is the relative clause. So inside this relative clause, there's a distant gap here. So completing this dependency is going to be harder compared to the object relative clause case, where the head noun has a gap over here closer to the head noun, right? So the distance between the gap and the head noun in the subject relative is larger than the gap and the head noun and the object relative clause, with the resulting prediction that object relatives are going to be predicted to be read faster at the head noun than the subject relative. Okay. So for example, in this Gibson and Wu paper in 2013, the key result was just one significant result, okay, one significant effect. And the claim was, I'm reading out what was in the paper, the head noun for the RC, this one, for this one here, was read more slowly in subject relatives than in object relatives. So that's the prediction pans out according to this statistical result, right? So this paper was published mainly because the result was statistically significant. And so indeed, we see the F1 score has a p-value less than 0.01, and the F2 score barely squeezes in with a 0.05 significance, right? What they didn't report in the paper was the min F prime statistic, okay? And if you do compute that min F prime statistic, you'll see that the result is actually not significant, okay? So those of you who don't know what this min F prime is, you should read this famous paper by Herb Clark, 1970s. It's about the fixed effect fallacy, right? So you should look at that paper. It's somehow been forgotten by the field. I don't know what happened. We routinely forget, the underlying statistical theory and just go our own crazy way when we do data analysis. And I'm talking about everybody in psycholinguistics, including myself. My PhD work also has, this kind of problem that I'm describing here. It's not just Chinese relative clauses. It's a very pervasive problem. And I have also made all these mistakes myself. Okay? So the mistake is to think that if you get a significant effect, so it looks pretty much significant here, you've actually learned something from the data, right? That you have actually a discovery claim that you can make. But that's not true. And I'll explain why, right? So the underlying papers, as I mentioned, there are two papers that from Ted Gibson's lab that deal with Chinese relative clauses. That's the original cognition paper. And the second paper appeared in LCN, as I said, LCP as it was called then. I don't have data for this first paper in cognition, so I can't actually show you the interesting details that might be there in it. But I will, even from the figures that they provide in the cognition paper, you can infer quite a lot, as I will show you, okay? So let's just focus on the data from this Gibson and Wu study because the data are available. Ted was good enough to give the data to me. So thanks to Ted for being so open, about all this. And I will come back to that point later, right? So what lies behind the Chinese data in the Gibson and Wu study? Okay, so what you see on the surface in the paper itself is this head noun here. This is a figure from the paper. And what you see is that indeed the subject relative is actually read slower than the object relative. So the black square has a higher reading time on average than the subject relative, than the object relative here, which is the white circle, right? Now, just looking at these summary statistics, these means and these some uncertainty intervals that they've plotted, I don't know what this is, maybe 1 times the standard error, probably. That's what it is, I suspect, right? So these estimates are actually hiding very important details. I mean, I'm not saying that Ted Gibson now deliberately hid all this. And I'm just saying that when we report summary statistics, I also report these. I have done this in the past, right? We actually lose a lot of detail in the data. So for example, in this particular data, what lies behind these two means and these standard errors is the plot that you're seeing, this box plot here. And what you should notice here is that the variation in the subject relative is much greater than in the object relative. Here in the object relative, the data are tightly compressed around the mean. And here you've got these extreme values, 6 seconds of reading times, that are going to have a dramatic impact on the mean of the subject gap. So what happens with the mean calculation is that the mean is extremely sensitive to extreme values. And I can demonstrate that very quickly, right? So if you, for example, if you try to compute the mean of 3 numbers that are roughly in the same range, right? 1, 2, 3. If I compute the mean of this vector, right, what will happen is that the mean is going to be 2, right? But if the third value is very extreme compared to the others, right, then the mean is going to be much, much larger, even though this one data point is responsible for the change in the mean. So the difference in the means, difference in reading time between these two conditions is going to be heavily affected by these two data points. That detail we forget when we do data analysis, right? We just plug in the data, run the data analysis, and we think we are golden. But that's not how life works, okay? So behind these means, there will be potentially interesting extreme values that you need to start worrying about, okay? All right, so but more interestingly, right, this 2013 paper was actually intended to validate the predictions of the original cognition paper, right? So let's go back and look at the cognition paper to see whether this difference, object relatives easier than subject relatives, this difference, does it show up in the original paper at all, right? So in the original paper, they had single and double embeddings. In the 2013 paper, Gibson had only single embeddings, right? The reason for that is probably clear to everyone, right? Double center embeddings in Chinese, nobody can understand, right? Not even Chinese native speakers, right? So this original paper in cognition, if you look at the reading time differences in object versus subject relatives, what you will notice is something very surprising. The pattern is exactly the opposite to what was in the 2013 paper. Object relatives are actually harder at the head now than subject relatives. That's the opposite to what we are seeing here. Yeah. So how can one conclude that the 2013 study actually confirms the predictions of the 2003 study? If anything, it's showing the opposite pattern, right? Now, the reason nobody actually knows this is that I suspect that people don't even read papers. So they just look at the title, right? They look at the abstract at most, and that's it. It's the Twitter world now, right? Nobody actually reads papers. That's all I can conclude from this, because nobody has noticed this point, It's a very surprising detail. But more importantly, the reason that the storyline about Chinese relatives has flowed in the way that it has is that the cognition paper came out in 2003 and a slew of other papers came out, including this 2013 paper, and they all had significant results somewhere, right? Some analysis done somewhere in the paper showed a p-value less than 0.05. Editor says, this is great. This tells us the truth is out there. We know what the truth is. And the authors also think that, oh, they found something. Yeah? But let's take a look at what actually happens now when you do that kind of reasoning, right? So the real problem in psycholinguistics, and it's not just Chinese relatives, it's basically everywhere. Pick up any random paper in cognition or JML, or just any, top class journal, even let's go to something like Perspectives in Psychological Science or Journal of Experimental Psychology, Learning, Memory, and Cognition. JP General, like just pick up any article in cognitive psychology and psycholinguistics, you will find that there is a single-minded focus on part of the reviewers, part of the editor, and the authors on statistical significance. That's what people care about, right? And what's interesting is that it doesn't even matter what is significant in the paper. As long as it's significant, it's good, right? So for example, there's a paper by Denberg and Keller, 2008, in cognition again. Cognition is a great place to look for, if you want to find nonsensical claims, that's a great place, right? So in the Denberg and Keller 2008 paper, they actually found a significant effect of dependency length increase, exactly the story that I'm telling you about Chinese relatives, right? Increasing dependency length should cause an increase in processing difficulty. That's the claim, and it's very well validated. That claim is pretty well supported. That's Ted Gibson's dependency locality theory. The story works very well, actually, overall. And so Denberg and Keller were evaluating this claim in that cognition paper. They had 10 subjects, okay, eye tracking data, and they found a significant effect of dependency length, but in the wrong direction. It doesn't matter. It's a significant effect. Who cares, right? So we publish it in cognition, and everyone, just goes on with life as if, we found something. But that's not how it works, right? Significance alone will not tell us anything about what's true and what's not true. Let me demonstrate this very important point to you, okay? So the whole problem actually rests with statistical power. Statistical power is the probability of detecting an effect that has a particular magnitude out there in nature, right? There's some particular non-zero effect out there that you're trying to detect. And so what's the probability of your detecting that? That's called statistical power. It's a probability, yeah? And so what we need to understand is that the frequentist method actually works really well when statistical power is high. It's only designed for those situations when statistical power is high. Whenever power is low, the whole frequentist paradigm breaks down. Okay, and that's the source of all this drama that I'm telling you about, this amazing saga of the relative clause story in Chinese. Okay, so here's the problem. This is the key point in this lecture now, okay? This talk. The point is this. So suppose that the true effect is 15 milliseconds and the standard deviation of the effect is, let's say, 100 milliseconds, which is pretty optimistic, actually, in self-paced reading, for example. Okay? And suppose that we run a typical psycholinguistic experiment with 20 subjects. Okay? If the true effect size is 15 milliseconds, right, power, you can compute this using power.t.test. Maybe I'll do this right now. Let's see. We have an effect size of 15 milliseconds. Standard deviation is 100. Sample size is 20. Okay. So what would be the statistical power here? You can compute this with the power.t.test function. What you do is the effect size is 15. Standard deviation is 100. Sample size is, what did I say? 20. And we are doing a one sample t-test. So the type of the test we are going to do is a one sample t-test, which is the same thing as a paired t-test, okay? So one sample t-test, and I'm going to say strict equal to true because I want to compute power on basically for a two-sided test, right? So if I compute power here, you see that power is about 10% here. That means you have a 10% probability of actually detecting the effect if it's actually there, right? Why would you even do such an experiment? But in any case, let's do this. So we're going to do 50 simulations now. We're going to run 50 simulations. And each time I'm going to compute the difference in means, right? We're trying to estimate this true effect. And I'm going to mark the estimate with a 95% confidence interval. And if the estimate is significant, I'll draw a circle. Otherwise, I will draw a triangle. The triangles are the non-significant effect. So what you should notice here in this simulation, the true effect is this horizontal line, okay? This solid line. What you should notice is that there's only a few significant effects in this study, in this simulation study. I've got 1, 2, 3, 4, 5, 6 significant effects out of 50 in 50 studies. But every time I get a significant effect, I get either an overestimate, right? the true effect is 15, but these estimates are grossly overestimating the true effect size, okay? Or in addition to getting an misestimate, I'm also going to get the wrong sign, right? That's the Denberg and Keller phenomenon from cognition that I mentioned. You get a significant effect, but it's in the wrong direction, right? That situation happens when statistical power is low. Okay, you get this oscillation of effects as you run an experiment, and you might occasionally get lucky in that you get a significant effect, but whenever you get a significant effect, the danger is extremely high that you're going to end up with an overestimate or even a misestimate. So Gelman and Carlin wrote a famous paper, 2014, in which they explained this point. And this, what they call these kinds of oscillations of effects is type M error. So there's a magnitude error and a type S error. So there's a sign error, right? You're getting the wrong sign. So the point of this slide is that when power is low, the significant effects are going to be meaningless anyway, because they're based on misestimates, right? Now, what would happen if you were using frequentist methods as they were intended to be used? So suppose now we have 350 subjects. Now the statistical power will be much higher. It will be 80%. And indeed, if you run the same simulation study, you will discover that most of the simulations show significant effects, but more importantly, the estimates are very close to the true value, right? So not only do you get significant effects repeatedly, you get accurate estimates, right? So that's the issue here, and that's why the whole Chinese relative clause saga has been such a big shit show, right? We're running low sample studies, and it's not just Chinese relatives. Basically, it's all over the place. We're running low sample studies, and we are ending up with misestimates that will not replicate. And in fact, even in the Gibson set of studies, you see that the results do not replicate. The original data at the head now show a slowdown for oblique relatives. In the second experiment, you see a speed up for oblique relatives, right? That's that classic oscillation of effects that you're seeing in a low power study, okay? It's fascinating, right? That we are so badly misled, by these frequentist methods. Okay. So what I want to show you now is that for the Chinese relative clause data, Gibson and Wu data, if I were to use their estimates to compute statistical power, taking into account the uncertainty of their estimate of the effect size, that is the difference between object and subject relatives, what I would find is that even with 50 subjects, my estimated power would be extremely uncertain. Power is a function, of three things: effect size, standard deviation, and sample size. If the effect size and standard deviation are uncertain, then you can take that uncertainty into account when computing the power. That's why you're seeing power as a distribution here. Right? So power is just a transformation of your power is just a function, of these parameters that we're talking about: the effect size, standard deviation, and the sample size. So if those are variable, then power will be variable too. And so for sample size 50, you see a lot of uncertainty about what your power might be. So you don't have any idea what power will be like. But as you see, if I increase the sample size to 300, I have relatively good certainty that I'm going to be in the high power range, right? But nobody runs experiments with 300 subjects. People run experiments with less than 50 subjects. Gibson and Wu was something like 37 subjects. Okay? So not even 50, right? And so that's the problem. That's the central problem that I want to unpack today. Okay? And so what I want to show you is what would happen if I were to use Gibson and Wu's estimates of the relative clause effects and all the variance components in their data, the between and within subject and between item variability. If I were to generate simulated data and look at the effect sizes generated under simulation, what I would find is that if the original effect size, so this is the subject minus object relative clause effect that Gibson and Wu observed, this vertical line, if I were to simulate data and compute the effect size each time, most of the time, the effect would be overestimated, right? So this is type M error in action. So the estimate that they got, along with its uncertainty, is going to lead to severe overestimation of the effect size. So this point I have discussed in another paper that I will point you guys to later on, right? So this is a paper that was published in Linguistics this year or last year. So I'll discuss this in a little bit, okay? So this figure is from that paper. All right, so now, as I pointed out, I'm only discussing Chinese relative clauses today, but it's not just a problem with Chinese relative clauses. This is a general problem in psycholinguistics. Okay? It's just an example. It's a case study of what's going on in psycholinguistics, including in my own work, by the way. I have made the same mistakes of running underpowered studies. Okay, so I'm not immune to this problem. Okay, so let me show you. Think about similarity-based interference effects. So this is the meta-analysis we did in 2017. Here are the typical sample sizes. Well, here, these are 20, 40 at most, I think. Rarely do we see experiments with 60 subjects. But look at what happens for a range of plausible effect sizes, right? If you have 20 participants, if this is the 95% confidence interval of the range of plausible effect sizes, this was a negative effect we were looking at for different standard deviations, what you get is power can at most be about 40%, right? With 40 participants, in the best case, power would be about 60%, right? And so you see that the problem is very worrying, that most of the experiments on similarity-based interference are underpowered as well, okay? This is the kind of stuff that I work on quite a bit. And so most of the studies are underpowered. Similarly, surprisal is such a big deal in psycholinguistics, right? But most of the published results are severely underpowered, right? So if you look at, there's a famous paper in the Journal of Memory and Language by Levy and Keller showing surprisal evidence for surprisal effects in German center-embedded clauses. And as I showed in this paper, which was also published in JML in 2018, as I showed there, if you assume a range of different effect sizes, the power in their study is fairly low for the sample sizes that they had. So they had 28 subjects, so approximately 30. Power is around 13%, under the assumption that the estimates that they found are actually reflecting the truth. Yeah, so we're using their estimates to figure out what would happen if we were to run that study again in future. And in fact, in this paper, if you look at this paper later on, you will see that I tried to replicate the Levy and Keller findings 7 times. Nothing. I found nothing. It's not surprising because this is type M error in action. Yeah? They got a lucky shot, right? They ran the experiment with 28 subjects, happened to get a significant result, and they thought they actually learned something from that, right? But no, that's not the case. Yeah. All right, so here's another example. This is a paper by Audrey Bjorky et al., also in JML 2020. And here, what Audrey and all the other authors, including myself, what we did was that we looked at the picture word interference paradigm, about 50 plus studies, and we computed power for a future experiment under different assumptions, taking the lower, mean, and upper bound of the estimates that we got from a meta-analysis. We look at the distribution of power under different assumptions, and what we find is that power is going to be dramatically low in the published studies for the sample size that people have used. Power is woefully low, and so the interpretation of the p-value is not going to be valid. We can't really conclude anything from the low p-value. So why is all this happening? Okay, all these people are trying to do the best they can. They're trying to find, the truth about a particular phenomenon. Nobody is engaged in any dishonest research or anything, right? Everybody's doing the best they can. What's missing is a basic education in statistical inference, right? So when we do, for example, if you decide to become a linguist, you take it as a given that you will learn syntax, you will learn syntactic theory, semantic theory, phonetics, phonology, pragmatics. All these things are part of your basic education. That's what makes you a linguist, right? But when we start doing experimental work, suddenly all bets are off, right? What we are taught is that, yes, you can learn how to set up a Latin square design and do an experiment, but the statistical inference is just a bunch of buttons that you need to press. And we get this number out, the p-value, and if it's below 0.05, you're golden. If it's above 0.05, stick it into the file drawer, right? And forget about it. Just keep running experiments till you get significant effects. That's basically how we are taught how to do data analysis, right? And me too. That's how I was also taught how to do this. So this is a very serious problem, I think, in psycholinguistics, that we have basically no idea what statistical inference is, and we have no idea how to use statistical models to do inference. Okay? So, and in fact, many people celebrate this simplicity, of the button pressing technique, what I call Mickey Mouse data analysis, just load the data, run a command or press a button and get your p-value. That's basically what we do, right? And so many people are very happy with this idea, right? So there's a post on Twitter, which has now been deleted. This post has been deleted, but you can always find these posts on the Wayback Machine, right? So basically, a former editor-in-chief of the Journal of Memory and Language wrote the following: doing statistics should be like going to the bathroom. Yes, you have to do it. Yes, when you do it, you want to do it right. But don't make a big deal out of it. Be careful about telling other people how to do it. And if your whole life is centered on it, there's something wrong, right? So the basic philosophical position that this person is presenting to the world, and this is an influential psycholinguist. This is not some obscure person sitting in India, who nobody knows. What this person is saying, that you basically want to be doing a quick and dirty job. That's what going to the bathroom would be, right? Doing a quick and dirty analysis. Right? You don't need to get into the nitty-gritty details of your data analysis. For example, if there's a few extreme values, in the object relative condition versus the subject relative condition, well, I mean, the t-test is going to tell you the truth. So just pull out the p-value out of that. And it's funny that it's called a p-value, right? Talking about the bathroom. I just realized that, sorry. But the thing is that if you think that statistics is like going to the bathroom, that is quick and dirty, then you should not be surprised if the data analysis turns out to be total crap. And indeed, as I tried to show you, most of the analyses that will be done using the frequentist paradigm when statistical power is low will be basically meaningless. They will be total crap. Right? They don't actually give you any information about the scientific question you're trying to answer. So it's actually in our interest to try to do better than this former editor of the Journal of Memory and Language, right? It is possible to do better work than this. Does it require dramatic amounts of statistical knowledge? No, right? Are you willing to spend a few months of your life studying statistics so that you are actually functional in doing this kind of work that you want to do? I would say yes, it's worth it, right? Many people will do just one semester worth of semantic theory and then go on and become linguists, right? That's basically what I did. Maybe I did 1 or 2 semesters, but I think 1 semester would have been sufficient for me to, finish my PhD requirements and get on with my life, right? So 1 semester's worth of work is certainly something that we should be willing to invest in order to do data analysis, right? It's not rocket science, okay? As I will point out towards the end. So what's the alternative to all this? The alternative to all this is to focus on uncertainty quantification. What I mean by that is that when you estimate an effect, what's interesting is not just the magnitude of the effect. What's interesting is how unsure you are of that estimate. When there is large uncertainty, what that is telling us is that the effect could have very small values or very large values. We don't know, right? So we have a lot of uncertainty about that estimate. We have a tight estimate of an effect, and that will happen when you have high power. That is the situation where you have a pretty good understanding of what the range of plausible values are of that effect. That's what I mean by uncertainty quantification. And in fact, as I mentioned, I have this paper here that you can read later on, in which I spell out this idea in detail. Obviously, in this talk, I can't do that, right? Okay, so as I mentioned, there are two papers that you should look at. The first one I've just mentioned. The second one is what the data analysis that I'm presenting right now is based on, some right ways to analyze psycholinguistic data. This will appear in the annual review for linguistics or something, some journal like that. But these papers are online on my homepage. Okay. So what's the alternative to doing this kind of p-value based research? In the frequentist paradigm, the way we do the hypothesis test, the ANOVA or the t-test or the linear mixed model or whatever, basically what we do is a likelihood ratio test. And what we are doing is we are computing a statistic which is -2 times the difference in the log likelihood between the null model and the full model. And what statistical theory tells us is that the distribution of this log of the -2 times the difference in log likelihoods, right? So the statistic -2 times the difference in log likelihoods has a chi-squared distribution as n goes to infinity, and the degrees of freedom is the difference in the number of parameters in these two models. And that's basically the theory there. It's an asymptotic result, right? The Bayesian approach is very similar. If you want to do hypothesis testing, the Bayesian approach uses something called the Bayes factor, which just takes the ratio of the likelihoods of the two models, which is just the same thing as the ANOVA. Notice that in the ANOVA, we are taking the ratio of the two likelihoods here, right? Here. On the log scale, this becomes a subtraction, okay? So in the Bayes factor, we also take the ratio of the likelihoods. The only difference is that we take the uncertainty of the parameters into account, right? And that's why we compute these, something called the marginal likelihood, which basically averages out all the parameters and their uncertainties when computing this likelihood. Here, what we do in the frequentist paradigm is we use the maximum likelihood estimate, the sample mean, to compute the log likelihood in the full model, right? So in the Bayesian approach, we actually take the uncertainty of that parameter into account, which gives you a much more conservative answer to the question that you're trying to answer, okay? There are other advantages to the Bayes factor, but those you can look at when you read the articles that I mentioned, okay? So let's go and look at the original paper, the Gibson and Wu 2013 paper. I'm just reminding you of the significant result there. I carried out the same analysis, took the same data set and carried out a Bayesian analysis of the Gibson and Wu data. And what I show you is that if we set up a null hypothesis to either be that the effect is zero, just like in the frequentist approach. In the frequentist approach, when we do a null hypothesis test, we assume that the null model is that the difference between the two conditions is zero, right? You could assume that. In the Bayesian approach, you can also assume that the difference is approximately zero, right? You can assume a distribution as well. It's more flexible in that respect. And so you can compare the null model with the full model. And the only difference in the Bayesian approach will be that the parameter of interest will have a prior distribution defined for it, right? So all the parameters in the model are also random variables. That's not the case in the frequentist paradigm. In the frequentist approach, we treat each parameter as having some unknown point value out there in nature, and we're trying to estimate that point value, right? So these details are not really important. What's important right now is to see that the Bayes factor actually gives me the ratio, the odds of one model or the other. So if the ratio is approximately 1, as it is in this case, for example, right? The ratio is approximately 1, What this tells me is that the null model and the full model are roughly equally good in explaining the data, right? So looking at this output, and of course, I have not explained all the details of this output here. That's discussed in the paper. You can look at that later, right? What I learned from this analysis is a slightly more nuanced picture, get a more nuanced picture about the data than the fact that the p-value is less than 0.05, in this kind of frequentist analysis, right? So my conclusion from a Bayes factor analysis would be that I don't know either way. I don't know whether object relatives are harder or easier than subject relatives given these data. And so for me, it's inconclusive. This doesn't mean that there is no difference between the two relative clause types. All I'm saying is that I don't know either way, right? Now, of course, trying to publish such a paper is going to be harder, right? But life is hard. If you want to find out something, you have to put in the work. You have to collect more data. You need to have more precise estimates. So just to say that, oh, but I won't be able to publish this result because it's not giving me conclusive evidence is not a good reason to stick to a frequentist analysis, okay? Unless, of course, one's goal in life is just to publish papers, right? If that's the goal, then sure. Of course, you can go around, doing the quick and dirty bathroom version of data analysis, and just publish results which are significant, because there the goal is just completely different. The goal is to publish papers. The goal is not to do science, right? If the goal is to understand what the truth is, then you have to put in work, right? That's life, okay? All right, so assuming, that you want to actually get to the truth and your goal is not just to produce papers so that you can get a job or something, right? I think it's a much better approach to use uncertainty quantification as your central goal when doing data analysis, and the Bayesian approach allows you to do that, right? So there are many advantages of using the Bayesian approach. First of all, whenever you have sparse data, you will get robust estimates due to the prior specifications that you will put into the model, right? This I've discussed in the other papers that I've mentioned just now. You can look at the details later, but I'm just giving you the high-level picture here, right? Another very important advantage is that you can actually build on prior knowledge, right? So now that we know quite a bit about Chinese relative clauses from the published data, even though the estimates are imprecise and noisy, we can still learn from that data, do a meta-analysis, use the estimate from the meta-analysis for a future study, so informing the new data with the previous data. That's something we don't do at all in psycholinguistics. I think a lot more can be done there. One other big advantage is that you can fit customized models, right? You don't have to be tied down to the Elmer type of model that you've got, right? So sometimes a mixture distribution is a better way to explain the data. You can define that very easily in the Bayesian framework, right? And as I mentioned, the focus is on uncertainty quantification. I already mentioned that, so I won't harp on that anymore. And more importantly, the Bayesian approach, the Bayes factor approach is going to answer your question directly because it will tell you the relative evidence for the null and the alternative model, right? The frequentist paradigm is designed to reject the null hypothesis, right? So once you reject the null hypothesis, you implicitly argue for the alternative, but you don't have any direct evidence for the alternative. In the Bayes factor, you're getting direct evidence for one or the other model that you're trying to look at. So the answer to your question comes directly from the model comparison, okay? There are important differences between the frequentist and Bayesian approach, which one needs to be aware of, right? So in the frequentist approach, parameters are considered to be point values. They're fixed unknown values. We're trying to estimate them. In the Bayesian approach, they're random variables. Parameters are random variables. So they have prior distributions defined on them. Importantly, in the frequentist approach, the entire hypothesis testing framework rests on the assumption that you might have done repeated replications of your experiment. You could have hypothetically done these repeated replications of the experiment, And so in that sense, the data are considered random, right? So the data set you happen to have is one instance of a multiplicity of experiments you could have done, okay? And all the inference is based on all those hypothetical data sets that you don't actually have, right? The Bayesian approach actually works with the data that you actually have, right? What you have is what you have. Once you have the data, it's fixed. It's not a random quantity anymore. There's no hypothetical replication assumed here. And we try to draw the inferences that we can given the data that we have. So there's a big difference there. As I mentioned, prior knowledge can be incorporated in the Bayesian approach, but not in the frequentist approach. That's a big disadvantage. And the focus on rejecting the null in the frequentist hypothesis is very misleading, because once you reject the null, you don't necessarily have evidence for the specific alternative you're interested in. You just have evidence against the null, and that's it, right? But the Bayes factor gives you a more direct comparison, right? And most importantly, for me at least, is the whole point about uncertainty quantification. Being able to talk about how unsure you are of the effect size is a very important thing. I discussed that in this article again. Let me mention this again: how to embrace variation and accept uncertainty. You can look at that article later. All right, so so these are, I just mentioned all these advantages, but there are some quote unquote disadvantages of the Bayesian approach. The first disadvantage is that you have to actually know what you're doing, right? We can get away with not knowing what we are doing when we do the t-test or the Elmer and so on, because we are taught, and I also was taught, to look only at one thing in the output, that is the p-value, right? So basically, when I did my PhD in 2002 at Ohio State, I just printed out those p-values, and that was it. So when I was trying to interpret the results, I didn't actually know what the model was. I didn't know what a linear mixed model was. I was just using whatever the statisticians told me to use. And so I don't think that this is the right way, to use statistics. You have to put in a little bit of work. And I'll talk about how much work you have to put in a moment, okay? You put in a little bit of work to make sure that you know what is going on with the model that you're fitting. Okay? So these ideas you need actually in the frequentist world as well. But in the Bayesian world, this becomes super important to understand before you do any modeling, right? And you do require some basic programming ability. So sometimes people complain to me that, why do I need to know how to program, right? In R, for example, when I'm doing data analysis. But if you don't want to do experimental work, then don't do experimental work. You can use intuition in linguistics and get pretty far, I think, right? But if you're going to do experimental work, you're going to have to learn all these things, okay? It's just part of the game that you have to acquire expertise in. Another issue with Bayesian approaches is the computational cost, right? So if you have very complex models, and I'm talking really complex, not like the subject and object relative clause stuff, right? Then you might sometimes need cluster computing, but this is easy nowadays. Even I can do this. I'm not like some hotshot computer scientist or something. So this kind of work can be done quite easily now, right? Now, the most important thing with the Bayesian approach, perhaps the thing that frightens people a lot, is that you have to actually think about your problem for the first time, through the process of developing priors for your parameters. You actually have to think about what the model means and what plausible values you could expect from a data analysis. For example, in the subject and object relative clause example from Chinese, I wouldn't really expect that the difference in the mean between the two conditions is like, I don't know, like 10,000 milliseconds. That is an implausibly large number, okay? So the values that you can expect between object, when you're looking at object versus subject relatives, are going to be constrained within a range. Right? That determines your prior for that parameter in the model, right? So you can elicit these priors from yourself through expert knowledge, through prior data, and you can also fit a range of adversarial models in the Bayesian paradigm to see what would happen if, for example, you took Ted Gibson's prior beliefs about object relatives versus subject relatives and some opposing point of view, which takes the opposite position, or some agnostic position, which doesn't have any opinion on what the difference should be, right? So all these things can be incorporated in the model. It's a very powerful tool, actually. Now, I come to the very important question of how one can actually learn enough to be actually to do data analysis. Well, there's some very good textbooks out there, right? So there's the McElrath book, which is a very broad and general introduction to statistical methods using the Bayesian approach. I highly recommend this book. If you're from the more from the psychology side, there's John Krishka's book, Doing Bayesian Data Analysis. We have written a textbook, which is on my homepage, that will be published very soon, that introduces Bayesian data analysis to psycholinguists and psychologists. It's designed for people like us, right? And in fact, I've also created a 4-week online course that you can do for free at this website. It starts on the 25th of January. And so you can sign up and do this course. And for example, this is the web page here, and you can enroll in this course, right? You can enroll in this course and do this once it starts. It's a 4-week course. That's not a dramatic demand on your life, on your time, right? You can do some quizzes, and you can even get a certificate at the end if you want to get one. And this will give you a basic understanding of the approach. And 4 weeks is not much, to be able to get a basic understanding of how to fit linear mixed models, right? In the Bayesian paradigm. You can also attend the summer school that we have every year. We've run it for 6 years now, and the 7th one will happen on the 11th, start on the 11th of September, 2023. It's a 1-week course which covers a range of topics in statistics. We have 4 parallel streams. You can do introductory frequentist methods, advanced frequentist methods, introductory and advanced Bayesian methods. So there are 4 streams that you can do there, right? So these are all the tools that are available. And of course, there are many other books out there. There's Bodo Winter's book, which doesn't really discuss any foundational ideas. So that's one problem with that book for me. But there are many other good books out there. There's one by Daniel Navarro, excellent textbook, frequentist approach. You can look at any of those and get a very good idea of the foundational ideas in statistics. Yeah. But you have to put in that work. You can't just expect that you can get away with just loading the data, running the code, and being done with it. Yeah. All right. So in closing, I want to thank Ted Gibson for being so open to having his data looked at. So he's one of the few people out there who's very open with his data analysis, and he gives you all the data that he publishes. You can get hold of it. This is a very general problem in psycholinguistics, that we generally don't like to share our code and data when we publish a paper. People don't do this usually, right? This is a serious problem because a lot of the published claims in the literature, if you look at the actual data that lie behind those published claims, they don't really pan out. They do not work, right? And so it is very important that other people be able to look at your data and your code to be able to evaluate under other assumptions, for example, whether the data actually support the theory that you're trying to present in the paper. This is just good science, It's nothing special or new that I'm asking for. I'm just saying that this is just good science if you just release the code and data with your published paper. And in fact, the Journal of Memory and Language in 2019 set a new rule, which was that when you publish a paper, you have to provide the data and code when you get the paper accepted in this journal, right? So the editor-in-chief of the Journal of Memory and Language, Kathy Russell, she was the editor at the time. She commissioned a paper from us. She asked us to look at all the papers that were published after this new rule was instituted in JML, and to check if the published papers were actually reproducible. That means, were the numbers that were produced in the papers actually reproducible if you had the data and the code and tried to produce those numbers again? So we looked at 59 articles. This work was done by my postdoc, Anna Lorena Vichute, and my PhD student, Himanshu Yadav. They took 59 articles published since 2019. So these were all the articles that were published since 2019. And they looked at whether they could produce the numbers that were reported in the paper. Okay, the statistics that were reported in the paper. So even under the most lenient criterion of being approximately 10% from the published numbers, right? What they found was that out of the 59 papers that they looked at, 8 just didn't provide any data at all. And some of the authors actually refused to give us the data, even after we asked them for it. Okay? This is after the policy has been instituted in JML. Okay? The remaining people who did provide the data, right, only 32 out of 51 provided the code. So 19 people didn't even provide the code. So we had to, so Anna and Himanshu had to, mostly Anna, had to rewrite write the code from scratch, given the raw data, right? And so the interesting result is that in the case where the code was provided, 26 out of 32 of the analyses were reproducible. That's the good news. So if you go down this path, you're going to produce reproducible research. There's not replicability that I'm talking about. I'm just talking about reproducing the numbers in the paper. Okay? But if you don't provide the code, then out of 19 articles, we only were able to reproduce 7 articles. You see the dramatic difference in these two leaves here, right? These two branches here, right? And of course, if you don't provide any data, then 100% of your data is not reproducible, okay? And so the problem with that is, why is it a problem that you cannot, if people cannot reproduce your analyses? The problem is that the possibility that one is misled by a particular published analysis is high. As I showed you in the Gibson and Wu data, right? The conclusions in that data do not hold up. Even if you analyze the data using the methods that we normally use, like linear mixed models and so on, right? So I will just show you that in a second, but I just wanted to make sure that you realize the importance of making data and code available. And Ted Gibson is a leader in this field in this respect, because he has always been very open about releasing code and data. So that's how everybody needs to be, right? You need to be able to make your code and data available. You should make it available. Otherwise, nobody will be able to understand what the facts are that we're talking about, right? So let me now demonstrate to you what the problems are with in the Gibson and Wu data, right? So let me first load the data. These data are available in a library that we created as part of our textbook that I mentioned earlier. So there's a data set there. Right, so if you look at this data, I've got DF, Gibson, Wu, right? So here I've got repeated measurements on 37 from 37 subjects, 15 items. There are 2 conditions, object extraction and subject extraction, and these are the reading times at the head now, okay? So I'm going to quickly recode the type column, which is object extraction and subject extraction. I'm going to recode this so that object extracted is coded as +1 and subject extraction as -1. And I'm going to just call this, I don't know, condition or something, okay? So this is contrast coding. If you don't know what that is, you should definitely spend some time thinking about contrast coding. We have a paper on this that you may want to look at. So let's see. Maybe this one here. Yeah. So you should take a look at this paper if you're not familiar with contrast coding. It's a very, very important topic, right? Especially if you're designing experiments with 2x2, 2x3, or 2x2x2 designs or something, right? Okay, so let me get back to my R code, right? So I've done this is some contrast coding that I've done. And so I would fit normally, what I would do is Ted Gibson in his paper used t-tests, right? But I'm going to use a linear mixed model. right? Because that's basically the appropriate way to analyze this data. Okay, so I'm going to fit a model with reading time. He used raw reading times to analyze his data. And so what I want to show you is that a simple linear mixed model like this, right? So if I try to fit a varying intercepts and varying slopes model here, and I hope you know what that is, right? This is the so-called maximal model that Barr et al. Talked about in 2013, right? I hope you guys know what I'm talking about, right? There's this famous paper. There's a famous paper. So there's a famous paper in JML, random effect structure for confirmatory hypothesis testing, keep it maximal. Dale Barr, Roger Levy, Christoph Schapers, and Harry Tilley, right? So this paper recommends that you fit the most complex model that you can, right? So let's try to do that, right? In this data set. So when I do that, I get a boundary singularity warning. What that means is that the variance covariance matrix, in this case of the items, so let's look at the output. You look at the output, you'll see the problem. There are several problems here. One problem is that in the items random effects, the correlation cannot be estimated. A +1 -1 correlation means that the optimizer is unable to estimate the parameter in both the subject and the item random effect. So these two parameters cannot be estimated because we have too sparse a data set, 547 data points, just not enough data to estimate those parameters. So we're going to simplify this model such that there are no correlations, and see if we can get away with this model now, right? Okay, so this model fits, right? And so let me look at the output now, right? Now, if you look at the output here, look here, what you see is a significant effect. In their published paper, they had a t-value of something like, by subjects analysis, they had maybe a t-value of 2.5, something like that. I don't remember now. Let's go back and look at the slides. What was it, if you remember? Yeah, so we had a, okay, so we had a F-score of 6.92. An F-score of 6.92 corresponds to a t-value of square root of 6.92, right? 2.6, okay? So the F value is t squared, from a corresponding t-test. So the t-value is 2.6. Here, the t-value is 2.1, already much smaller. And that's because the model is taking all the variance components into account. But more importantly, this significant effect is coming from the fact that you've got these two extreme values here. If you downweight these two extreme values by taking a log transform, let's take a look at what happens. Okay? Let's do this. All right, so I'm going to refit this model, downweighting those extreme values. Okay. Now, if I look at the output, my result is no longer anywhere near significant. Right, so there's still a warning because this variance component is 0. So let me remove that variance component. Okay. I'm going to remove this variance component here. And so let's fit this model and look at the output. Notice that I have a non-significant effect here. So what I'm trying to show you is that even under the data, even given the data that was in the Gibson and Wu data set, there's actually no evidence for a significant effect. And the reason that one gets a significant effect is that one ignores the model assumptions, right? That's one problem. The other problem is that extreme data in the object relatives. The third problem is that it's a low power study. So even if I had run this analysis and ended up with a significant effect here, that effect would have been based on an overestimate of the effect size, right? Now, when I say the model assumptions were not met, What I'm saying is that the data were analyzed as on the raw reading time scale, which is done very commonly, actually, right? Psycholinguists do a lot. And in fact, there's a tweet by Roger Levy in which he says that you should analyze the data on the raw millisecond scale because the normality assumption of the residuals is the least important thing in a linear model. Well, it's the least important thing in a linear model the way a cricket ball is the least important thing in a cricket match, right? If you don't have the ball, you can't play cricket. Doesn't matter how good your players are, right? And so Roger Levy in his tweet has actually said that Andrew Gelman recommends that you don't care about the normality assumption, but that is incorrect. Andrew Gelman does not do hypothesis testing, right? So when you do hypothesis testing, these assumptions really matter. Even Gelman would agree with that. He has a blog post correcting his point, clarifying his point. You can look at that later on if you want to. But so many psycholinguists and even really influential people like Roger Levy say this, that you should not care about the normality assumption. That is completely false. In hypothesis testing, the normality assumption is a crucial part of the argument. The normality assumption actually is not important if you're just estimating the parameters. That is true, right? That's the Gauss-Markov theorem. But if you're doing hypothesis testing, the normality assumption is crucial, right? So that's why log transforming the data here or finding some appropriate transform of the data is very important when you're doing data analysis, right? So, and I mean, if you use raw reading times in this kind of data analysis, right, what will happen is that the model that you will generate will actually predict negative reading times. The model predicts that you can produce negative reading times. This should be very worrying for you, because if the model doesn't even make sense for the data you're analyzing, why are you using it for statistical inference, right? Statistical model is a model of the way the data were produced, right? And so if the model is nonsensical, you should question the assumptions there. So that's why I just log transform the data. And so what I get out of this model, if I'm focusing on significance alone, which of course I'm not, right? But if I were to do that, I would have to report a non-significant result, even given those data, right? And even as I showed, even if I don't log transform the data, right? So where was it? Sorry, what did I need to do here? This was the model that converged, right? Yeah, this was the model that converged. And so here, I might think, oh, I've got a significant result here, right? You might get overexcited about that significant result. But as I've tried to explain, that significant result is a type M error. If you try to redo that very same experiment, and you're welcome to try this, redo this study in China, for example, with say 300 subjects, and I guarantee you that you will not get an estimate in this range. I can guarantee that, okay? Okay, so that's the basic story that I wanted to tell you guys about relative clauses. It's just a cautionary tale, and it applies to pretty much everything out there. Please, when you do your data analysis, be very careful about the statistical properties of your model, right? Whether the model assumptions are met. Make sure that you have sufficient statistical power if you're going to do a frequentist analysis, right? Power analysis is something I show how to do in this paper. In many papers I've got online, you can find sample code for doing power analyses, right? You can look here. And I think I also did the power analysis in this paper. This other paper that I mentioned, some right ways to analyze psycholinguistic data. So do the power analysis before you run the experiment. Know how many subjects you need to get sufficient statistical power, and then it's fine. Then you can do this frequentist analysis. Now, nothing wrong with the frequentist approach per se, but if you're in a situation, often we are forced to analyze data that do not have sufficient power. There you need to think much more carefully about how you're going to analyze data and what conclusions you can draw from it, right? And the Bayesian approach has some advantages, when you're working with this kind of sparse data problem, provided you can come up with reasonable priors. So I discuss all this in these articles, so you should look at this work later on. So that's the main point of this talk now. And I only use the Chinese data to demonstrate the type and scale of the problem. But as I mentioned, this problem exists in pretty much every data analysis that you will see in a published paper. There are, of course, a few phenomena like garden path effects and so on. Those are such big effects that there, even with 40 subjects or 20 subjects, you can easily detect, those effects. There are a few effects like that do not require large sample sizes. But if you're studying subtle things like Chinese relative clause, reading time differences, then you have to pay a lot of attention to the model assumptions, to the power properties of your design, and to the inferences that you can draw from that data. Yeah. All right, so that's pretty much all I wanted to say in this talk. And as I mentioned, after you listen to this recording, I'll be available for about an hour for a live question and answer session. Thank you.